Hello, this video tutorial will show you how to implement a line following robot using VREP, the Virtual Robotic Experimental Platform. This video tutorial is based on a previous recording of a seminar that showed you how to modify a simple Ackermann steering robot and add bump sensors to it. The previous seminar is not a prerequisite for this tutorial, and the concepts that I will show you in this video can be applied to any robotic platform of your choosing. We begin this tutorial by adding a path to the workspace for our robot to follow. We right-click on the workspace and select Add, Path, and then Segment Type. Sorry, it's in the way. Add path segment type. You see now here the path has appeared as an object in the scene hierarchy. We right click on it, select Edit, Edit Modes, enter Path Edit Mode. This is the path edit mode. The scene hierarchy has disappeared and you now see a list of path points that are part of the path. This is the path editor dialog. The first thing we're going to do, we're going to zoom out and you'll see that the simulator just added some default points. We will delete point 2 and we will move point 1 to somewhere where it's less cluttered. We select Object Item Shift, and then we can just drag the path point away. So with path point 1 selected, we right click and then select Insert New Control Point after selection. It generates a path point right on top of the first path point. We select Object Item Position Orientation control box, and we will translate the path point. Down here in the corner you will see the orientation of the X and the Y and the Z, and it shows you which direction is the positive of those coordinate axes. We will translate the point 2 meters in the positive Y and then click Translate Selection, and you will see that the system has connected the path points. We can then drag and drop the points around, and so sort of create the path as we go along. Now when you're adding points to the path, be sure to have the last path point selected, otherwise it will only give you the option to insert a new control point at the beginning of the path. So, but if you have the last path point selected, you can insert a new control point after the selection, which allows you to add points or delete points in the center of your path. You can also see that the system has interpolated some corners, and I will show you shortly how to edit the radius of those curves. Okay, so now we built all our points, and because we want this robot to go in circles, we select path is closed, and it will automatically connect the last point to the first point. So the simulator has interpolated between the points and has created some round curves. What we can do here, we can select a couple of points and let's change the radius. And the way to do that is to change the Bezier interpolation factor. It takes a value between 0.1 and 0.99. Let's try 0.1. And then we click apply to selection. And then we see that these corners are all of a sudden very sharp. Not many robots will be able to traverse them perfectly, and it's really up to you to check with the competition guidelines what is the minimum radius that will be given to you. So let's change it to 0.99, and you will see that these corners are now very large and easier to traverse for many types of robots. Since you're using a Ackermann steering car, they are a little bit less agile when it comes to corners. So we'll have to set the corners. We'll actually set all of the corners quite large. Okay. When you're done creating the path, you select the X to close the path editor, and when it asks you do you wish to apply the changes, you select yes. Now you have added the path to the workspace. Currently, the path is a virtual object in your workspace, and we need to make it a renderable object. In the scene hierarchy, you have to double click on the path icon, and it brings up the scene object properties. We then select show path shaping dialog and select path shaping enabled. Right now it has generated a renderable object, and we'll first adjust the color, and in our case we're going to be using a black line that the robot has to follow. We select adjust ambient component and put RGB to 0. Close the dialogs. Now currently, if you zoom in, you will find that your path is a circular object, and you can change that by clicking on the section characteristics and selecting a horizontal segment. So now it's flat on the ground. You can also select it as a square depending on your preference, but currently as it is, the robot will drive over these bumps and it will affect how the robot responds. So we'll select a horizontal segment. The only thing that is left to do is to select the scaling factor. Now, this will depend on how thick of a line you want, and you will have to experiment with this number to check that the line thickness is how it is relative to your car. And once again, this is a number that you have to confirm with the competition that you're designing this robot for. So when you close all of these, just a second actually, before we close the scene object properties, we will unselect show path line. What this does, it will remove this outline of the path line and hides it. Then we can close this And then now you have created a path for the robot to follow. The next step will be to move the robot itself somewhere onto this path line and to implement the vision sensors. To add a vision sensor to the environment, we right-click, select Add Vision Sensor, and then it gives us two options, orthographic type and perspective type. To see the difference between the two, we consult the manual, and it shows us that the perspective type has a trapezoidal viewing area. The perspective projection essentially has a single point, which is the center of projection, whereas the orthographic projection type has more of a large area that is the center of projection. The orthographic type can be thought of as a spotlight. We will assume that our light sensor is of the orthographic type, but that really depends on your hardware. So we select Add Vision Sensor, Orthographic Type. So now it has selected a vision sensor somewhere in the environment, and we'll have to go and find it. Actually, what we will do instead, we will select the car, select position, and then select Apply to Selection. And then it brings the vision sensor from wherever it was in the environment to where the car is. Okay. To see the output of the vision sensor, we would like to add a floating view. We'll select the scene. We'll press Escape to undo any selection. Right click, select Add, and then Floating View. This creates a sort of view that that is a window, and we will associate the vision sensor with that floating view. We with the vision sensor selected, we right click on the floating view and select View, Associate View with Selected Vision Sensor. We now see and hear what the vision sensor sees. When we run the simulation, we can find that the vision sensor is actually looking straight up. That's why our view is black. So we will have to change the properties of the vision sensor and reorient it. Okay, with the vision sensor selected, we select the object item position icon, and then relative to its own frame, let's move it around. Actually, I should not have done that. Let me just position this. Okay. So along the world coordinate frame, we will move it along the Y by 0.1 meters. And we can do this a couple of times. And now we'll move it centimeter by centimeter. And when we think that it's approximately correct, we can also rotate it by clicking orientation/rotations, and on the world coordinate we select gamma by 180 because we wanted to point down, and then click rotate selection. This did not do what I thought it would do, so we just click undo, and we'll just rotate it around its own frame. Around X by 180, and you can see the red line, which is its own X direction. So if we rotate it around its X, it should point straight down. Okay, so now we're still seeing black, but this could partially be because it's currently looking at the line. Okay, let's examine the vision sensor properties a little bit. In here you can see this blue outline, and that's the near and the far clipping plane, which tells you just how far, what is the minimum distance and the maximum distance that the vision sensor sees. I will illustrate that by changing this to 0.2, and now you see that this changed. This is kind of to give you a region of interest, and we don't need this to be quite so far, and we'll change the far clipping distance to 0.1. Also in here is the perspective angle and orthographic size. We have the resolution in the XY, which is currently 32 by 32 pixels. We also have the object size, XYZ, and so on. What I'm going to do next, I'm going to attach the sensor to the car. I will select the car, right click, and then edit, make last select object parent. So now the sensor is attached to the car, and when we run this, we find that the vision sensor is looking at something, and it temporarily turns black when it crosses our path. Now, since it's we're using a light sensor, why don't we change the vision sensor? The vision sensor resolution does not have to be quite that big, so we'll change it to 4x4, which will make it really blocky. But since we're using a vision sensor, we could technically make it 2x2 or 1x1. But let's leave it as 4x4 for now. Alright, let's move the car slightly so that the vision sensor and you could see briefly that the vision sensor was saw part of the line. Okay, we'll rename the vision sensor as middle light sensor, and since we like its current configuration and we don't want to have to go through all the hassle of redoing it, we can actually select edit, copy selected objects, and then edit, paste buffer. It will paste the same type of object into the world coordinate space and call it vision sensor 0. Oh, I did not rename that. Let's rename it middle light. Okay, so I will rename this right, light, and then I have to also move it around. And in this particular scenario, we're using 3 light sensors. Relative to its own frame, I will shift it along X by 0.1, which maybe is a little bit much. I'll shift. My concern is that it might interfere with the bump sensor, so I'll shift it back by minus 0.1. Sorry, 0.1. Okay. And again, we have to attach it to the car. Edit, make selected object parent. And then we have to do this one more time. Copy selected object. Actually, I would like to copy the middle. And then translate it. And I believe it was around minus 0.08. And now it should be symmetrical. We'll call this one left. And again, we attach this sensor to the car. It would be a little bit tedious to show all of the sensor outputs in floating views. So let's add a graph to visualize the intensity of these light sensors. We right click on the workspace and select add, and then graph. Now a graph has been added to the workspace. We would like to show the simulation as a split screen. So we select here this icon, page selector, and then we select just any page 1 is our current view. We'll select page 2. We right click and then select remove page to create a blank page. We right click and then say set up page with 2 views horizontal separation. Now this gives us 2 windows. We select default camera, right click on it and select view, and then associate view with selected camera. We then right click the bottom half, we select graph 0, which will be the vision sensor output. We right click the bottom pane and then select view, associate view with selected graph. Now we have to select, now we have to edit the graph properties to show us exactly what we want displayed. We right click on the graph icon under add new data streams to record. Under the data stream type, we scroll down to vision sensor, and it gives us a large range of potential types. And we will select vision sensor average intensity value, and from the object it only allows us to select our 3 vision sensor. We select the middle one. We will rename this as middle. And then we have to do the same thing for the other 3 sensors, for the other 2 sensors. For the right one. And it always pays to rename it, otherwise it will be shown up as data. So this was the right. And currently they're both red, so we'll adjust this one and make it green. Let's add the other one. And again adjust the color, and this one will be blue. Okay. So let's zoom out of this view. And then position the car. And then we can run it and then see what happens. Okay, so on this graph here, you see the average intensity values of the vision sensors. You can see blue, which was the left one, hit the line first and it went down to nearly zero, followed by the red, which is the middle one, and then the right. And then there was nothing for a while, and then again as it hits the line on the other side. You will notice that there is a change in average values going from here to from the time before 3.5 seconds and after about 3.5 seconds, and that's because the tiles are differently colored and it shows you the average intensity value. These values can be used within your programming to find out what exactly the car the values of the intensity values that correspond to your line are. For example, if you had any different color, your average intensity value would be different. Now that you have created a path and modeled the sensors and know what the sensors are reading and have verified that the readings are correct, you can now begin and implement the sensors as part of your control strategy for the Ackermann steering car. We double click on this icon right here, which will bring up the script associated to the Ackermann steering car. If you wonder what other types of script there are as part of your model, you can look over here where it says scripts, and it shows you all of the main scripts and child scripts associated with all the objects. Most of them are have been added previously, so we won't really do any changes there. The first thing we need is to get an object handle into the script. Over here I have defined all of the object handles, and down here I have a while loop. So let me define vis_l equal to sim get object handle. Now, while you're typing, it brings up a whole bunch of suggestions, and you can use the up and down arrow keys to select or even just to look through all of the different functions that are available. If you have selected if you have found the function that you're looking for, you just press enter and it will auto-complete it. It needs a name of the function, of the object that you're looking for, and the name is just as it appears in the scene hierarchy right here. Since we're looking for the left vision sensor, we're going to call it left_light. Now we have a way of finding the object within our loop. So we go through this loop, and this is the one that we've previously designed in our in the bump sensor tutorial. And we'll scroll all the way to the bottom, and then we'll add another sort of behavior. I've already done this before, so I'll just type it out. Results, comma, data equal to sim read vision sensor, and I'll use viz r, which is the right vision sensor. The following function returns two variables, result and data. In data, it stores a whole bunch of information about the vision sensor, and the result will show you, it's I believe just a boolean or a number, 0 or 1. Now this is where it gets a little bit complicated. To find out what the sim read vision sensor returns, we're going to have to check out the vrep manual, which we can access by clicking on help topics, which brings up the manual. This is a very good resource if you are ever curious. It also has a couple of tutorials here at the end. But what we are interested in is under scenes and models. This does not seem to work on Internet Explorer. I'll just switch. Under entities, we scroll down to find vision sensors, vision sensor properties. Just a second. Oh, here, under related API function. So we click vision sensor, scroll all the way down, related API function. This shows you all of the function that you can call using the handle to identify. And what we are interested in is sim read vision sensor. Now this manual is a little bit complex in how it chooses to represent the return functions. So under auxiliary values, which is our data function, it packages certain information, and the way it packages it, since we haven't added anything, by default it packages it in the following. It returns an array of about 15 entries. By default, let me read this here. By default, vrep returns one packet of 15 auxiliary values. So the first 5 are the minimum of intensity, the red, the green, blue, and the depth value. Then the maximum of intensity, red, green, blue, or depth. And then what we are interested in is the average of intensity, red, green, blue, and depth. So the average intensity is located at entry number 11, and if you remember, in this graph we're graphing the average intensity. So here we can say if data at 11 is less than, don't forget the brackets, is less than, and then here we have to consult the graph, and I'll make a cutoff value of about 0.2. Is less than 0.2, then, and what we'll say is desired steering angle is equal to, and now we'll just pick a value at random, minus 10 times math.pi divided by 180. And here we're putting the desired steering angle into radians. And so now our robot should drive along until the entry of the right sensor reaches 0.2, and then it should turn either one way or the other. And then let's test what happens. Okay, so for some reason it started turning right away, and this could have a couple of reasons. There is a sudden spike here which brings the value down to 0 at the beginning of the simulation. This is most likely explained by the fact that the car drops down a little bit if you look closely here. And clearly somehow it must the values get outside of the readable maximum and minimum. So what we do here, one way of fixing it, we could probably drop the car down to the level ground, or what I have chosen to do is to check whether the simulation time is greater than 0.2 seconds, so that we don't get any effects of the beginning of the simulation. So I put this actually into another if statement. If sim get simulation time is greater than 0.2, and again don't forget the brackets, and proper indenting as well. I'm not sure whether the proper indenting is mandatory, but it's always good practice. Alright, so let's check the behavior of this car now. Okay, so now you could go through and do the same thing for the left and the middle sensor and figure out what sort of combination of threshold values and steering angles will get you the best result while you're going around a loop like that. So now you have everything you need to model a line following robot in the VREP environment. You know how to draw a line in the environment, you know how to add sensors to your vehicle, you know how to read the sensor inputs and visualize them in a camera window, and you can also read those sensor inputs and put them as part of your steering script. But I'm not quite happy with the results just yet. Currently, as you can see, as you drive over the line, you can tell where the line is in 3 locations. You can tell if it's either left, middle, or right. And that's because we chose to model our sensors as orthographic sensors. I'm not entirely happy with that, and we can actually change it by checking perspective mode, and now you can see you have a much wider view. And as far as the pixel goes, why don't we give it an 8 by 8? And we'll do the same for the right and the left sensors. Let me also temporarily turn off this the steering angle, This is the average intensity values before we changed the sensors, and you can see that this is quite steep. Now when we drive over the line, you see that there is actually now some overlap in between the sensors. This is very good because now we can or you can try to estimate the location of the line based on what the reading is and whether there is a combined reading. You can also play around with moving them closer together. What this will do, it will allow you to get the line, rather than from a discrete state of being either middle, left, or right, to more along where you can say it's either here, here, or anywhere within this area. This should allow you to get a lot better control and should help you design your robot better. I can't really tell you exactly how to do that, but you could try setting up experiments where you move the line relative to your vision sensors and see just how much overlap you get. And this concludes the line follower video. Thank you for watching, and if you have any questions, please leave them in the comments below. Thank you. And now, just as a bonus, let me show you what an implemented line following robot looks like. Now you can see that to successfully traverse the line, it's a combination of the robot speed and the robot steering angle. You can of course also make it a little bit more fancy by allowing it to either accelerate or slow down in certain areas. And as you can see currently, my steering angle is not big enough for the speed at which the robot is going. However, it seems to be doing alright. Well, I wish you good luck with your robot building and your robot design. Thank you for watching.